This video presents our work on meta-learning via learned loss. Meta-learning originates in the concept of learning to learn. The goal is to learn how to efficiently optimize a function f, which could be a policy, regressor, or classifier, parameterized by theta, to find the optimal values of theta. L is the loss function, and h is a gradient transform. The majority of work in deep learning is concerned with learning f from data directly. Some meta-learning work focuses on learning optimizer policies that perform parameter updates. Yet other approaches meta-learn directly initializations of model parameters theta. Our approach falls into the category of loss learning. Loss functions are preferable since they are architecture independent and widely applicable for a variety of learning problems. Learning loss functions also has the benefit of not having to tune the loss function manually, and that it allows the inclusion of additional information, for example expert information, during meta-training. Our approach of meta-learning via learned loss includes a function f, parameterized by theta, that takes as an input a variable x and outputs y. We also learn a loss network m, parameterized by phi, that takes as an input the output and input of f, together with some task-specific information g, for example the ground truth label for regression and classification problems, the final goal position of the robot joins in model-based reinforcement learning, or the sample reward for model-free reinforcement learning problems. M then outputs a loss L that is parameterized by phi but also by theta, since the output of f is an input to M. To update f, and since L is a function of theta, we compute a gradient of L with respect to theta, and perform a gradient update using our learned loss function, giving us the new and currently optimal parameters of f, given the learned loss. To update M, our loss network, we formulate a task-specific loss that compares the output of the currently optimal f with the target information. Since f was updated with L, the task loss now is also a function of phi, and we can perform a gradient update on phi to optimize M. This leaves us with a fully differentiable loss learning framework that can be used after training to directly update f by taking the gradient of the learned loss L with respect to the parameters of f. Now we're going to present experiments showcasing the applicability of our learned loss. The first experiment is to fit a sine curve, a classical regression problem. During meta-training, we train on one sine example and see that using our loss fits the sine curve more accurately compared to the MSE loss. During test time, we use our learned loss to fit a variety of sine curves that have not been seen during training, and see that we outperform standard MSE loss while needing less training data. For our MNIST classification experiment, the results are very similar. We train on two classes and see that we achieve higher classification accuracy during train time. Again, we test the learned loss on previously unseen digits and outperform standard MSE on these new digits as well, when using our learned loss to train the classifier. Another advantage of learning a loss function is the flexibility to include additional expert information during meta-training. That, for example, allows us to shape a loss landscape such that it is easier for optimization. This experiment is concerned with fitting the frequency parameter theta of a sine curve, and during meta-training time we assume expert knowledge of the ground truth frequency parameters of the data, theta star. The loss landscape of standard mean squared error for this problem is highly non-convex. With many local minima, the optimization could get stuck in. Our loss, however, using the extra information, shapes the loss landscape nicely, creating a loss landscape that is easy to optimize with gradient descent. Loss shaping can also be used to include additional goals into the learning loop. Here we show results for a classic control problem, the mounted car, where the car tries to drive up the hill but the engine is too weak to climb the hill by accelerating. Using a standard MSE loss between the current state and the goal state results in the car driving up the hill but never reaching the goal. Our learned loss is shaped by adding a goal on the other side of the hill during meta-training, effectively shaping the loss landscape to inherently explore the opposite side of the hill. We also use our learned learning framework for model-based and model-free reinforcement learning problems. In model-based reinforcement learning, the model of the dynamics of the robot P is learned and used to optimize the policy. The reward is computed through the model, and we use the cumulative reward as task loss during meta-training. We learn our loss using only two targets during meta-training. After training, the learned loss can be used to directly optimize the policy. The dynamics model is not necessary during test time anymore. The loss learns to implicitly represent the gradients of the dynamics of the robot and can produce a loss to optimize the policy directly. The 4 targets shown here have not been seen during training, showing the generalization capabilities of our approach. For our model-free reinforcement learning experiments, we used a modified version of the Mujoko Gym and Reach environments. The results of the experiments show that using our learned loss to optimize a policy is 5 to 8 times more sample efficient compared to PPO, a standard off-the-shelf model-free reinforcement learning algorithm. We also tested the learned loss on different policy architectures, and we can see that ML3 generalizes well to new policy architectures. Code to reproduce the experiments is available on our website. For more experiments and analysis, please refer to our paper. Thank you.